Hello, my name is Jin, and today I'm going to talk about my joint work with Yinzhan Xu. This is a paper on fine-grained complexity, and the title is Removing Additive Structure in Threesome-Based Reductions. In the threesome problem, we are given a set A of n integers, and let's suppose they come from a polynomially large universe. And the goal is to decide if these integers contain three of them that sum to 0. In the literature, you might have seen several other definitions of threesome, but you can show that they are all equivalent under fine-grained reductions. The threesome problem has a very simple n-squared time algorithm, but currently the best-known algorithm only improves it by a polylog n factor, and this has led to the threesome hypothesis, which conjectures that there is no truly subquadratic time algorithm solving threesome. This is one of the three central conjectures in the fine-grained literature, and it has a lot of implications in conditional lower bounds. In this work, our contribution is to prove new lower bounds from the threesome hypothesis for various problems using techniques from additive combinatorics. Let's first talk about our main technical result. First, we need the definition of a Seidel set. This is a set of numbers that avoid non-trivial solutions to this Seidel equation, a plus b equals c plus d. Here are two examples. The first example is not a Seidel set because it contains a solution 1 plus 5 equals 2 plus 4, while the second example is a Seidel set. Then our theorem 1 says that assuming the threesome hypothesis, solving threesome on the Seidel set is already requires quadratic time. So the main message of this theorem is that threesome instances with no additive structure are the hardest. Here, additive structure is kind of an informal notion, and we can understand it by looking at these two extreme examples. Suppose we sample a bunch of random numbers from a large range, then we can say that this set of integers have no additive structure. They are pretty random. On the other extreme, suppose we have an arithmetic progression, then they are spaced apart at equal distance, and they contain a lot of additive structure. One way to quantify this intuition is to look at the additive energy of this set of integers. The additive energy is defined as the number of solutions to this Seidel equation, where the four integers are coming from this set. The maximum possible value of additive energy is up to a constant size a cubed, and this is indeed achieved by an arithmetic progression. On the other hand, suppose we have a random set of integers, then it's likely that none of the four tuples of integers actually satisfy this equation, except for those trivial solutions. So in this case, this set achieves the minimum possible additive energy, 2a squared minus a, and it is indeed a Seidel set. So our theorem 1 says that the threesome problem on a Seidel set is already as hard as the general case. So this could be very useful for designing fine-grained reductions from the threesome problem, because instead of starting from arbitrary threesome instance, we can conveniently assume that the instance we have is a Seidel set, which we'll see can be very helpful. So for the rest of the talk, I'll first talk about applications of our theorem 1 in fine-grained complexity. This includes some lower bounds for some graph problems and another problem called for LDT. Then I'll talk about proof ideas for our theorem 1. Here I need to mention that the first two applications were also independently obtained by the paper by Aboud, Breman, and Fisher, which also appears in STOC this year. They prove the results using very similar techniques. Now let's look at our applications for the graph problems. In the literature, there are a lot of graph problems that are shown to be threesome hard, and most of these results are proved by first going through a reduction from threesome to some triangle problems, namely triangle listing or all-edge triangle. And this first step was established in an influential paper by Patrashko in 2010. Here, the all-edge triangle problem asks for each edge E in an undirected graph, whether this edge E is contained in some triangle of the graph. And Patrashko's result says that on a graph with maximum degree root n, it requires quadratic time to solve the OH triangle problem or the problem of listing n to the 1.5 triangles, assuming the threesome conjecture. Very recently, the paper by Abud, Brinkman, Khoury, and Zamir from STOC last year showed threesome hardness for some new problems, including C4 listing and approximate distance oracles. And they obtained these results by going from the OH triangle problem and using a new framework called cycle removal to perform this reduction. And in our work, we improved the results. Now let's take a closer look at these two problems. So given an undirected graph, the algorithm by Alon user and Zwick can detect whether this graph contains a four cycle. The four cycle is not required to be an induced four cycle. And this algorithm runs in minimum n squared and m to the 4/3 time. And this detection algorithm can actually be converted into a listing algorithm. Given an additional parameter t, the algorithm can find t different copies of four cycles in this graph. And the previous work by Abud et al. Showed the first non-trivial lower bound for this C4 listing problem. They show that no m to the 1.19 plus t time algorithm could list t4 cycles under the threesome or APSP conjecture. This was the first superlinear lower bound for this problem, but there's still a gap on the exponent between upper bound and lower bound. In this work, we close this gap, showing that essentially both this n squared dependency and the m to the 4/3 dependency are actually necessary for this C4 listing problem under the threesome conjecture. The next application is about distance oracles. This is a problem that was studied by this celebrated paper by Thorup and Zwick in 2001. They show that for constant integer k, you can preprocess an undirected graph G in m times n to the 1/k time and obtain a data structure that supports 2k minus 1 approximate distance queries in constant time. A curious question is whether it's possible to improve this preprocessing time, for example, on sparse graphs. This question was studied by the previous work of Abud et al., and they obtained the first non-trivial superlinear lower bound on the preprocessing time. The lower bound was m to the 1 plus 1 over 12.8 times k. So they got the right dependency on k up to a fairly large constant factor. And in our work, we improve this dependency on k from 12.8 times k to only 2k minus 1. But our result is still not tight. There is a gap between 2k minus 1 and k. Now, let me explain how is our theorem 1 useful in obtaining these improved results for these graph problems. And to see this, we need to first look at the framework by the previous paper by Abud et al., the cycle removal framework. Let's first look at a very natural attempt to reduce from the OH triangle problem to the listing C4 problem. Let's say the triangle instance is a tripartite graph. Then we can split one of the vertex parts into two parts and connect them by a matching. In this way, a triangle in the original graph is mapped to a four cycle in the new graph. So a C4 listing algorithm on the new graph can potentially be helpful for finding triangles in the original graph. However, this approach has an issue due to these fake solutions. So there can be some four cycles in the new graph that do not actually correspond to triangles in the old graph, but rather they correspond to four cycles in the original graph. So if the graphs contain a lot of four cycles, then this can be very bad because the listing C4 algorithm could just output these fake four cycles without actually helping us find triangles in the original graph. To overcome this issue, Abud et al. Developed this cycle removal framework they remove the edges of the graph in order to decrease the number of force cycles, so that less time is wasted on listing these fake solutions. And this has to be done in a very careful way, so that they can also efficiently find the triangle solutions involving these removed edges. So let's look at the parameters achieved by the cycle removal framework from the previous paper. Starting from an all-edge triangle instance with maximum degree root n, initially there could be as many as n to the 2.5 many force cycles. This is the maximum possible number of force cycles in a root n degree graph. And after the cycle removal framework, the cycle count is reduced to n to the 2.25. And from there, they switch to a different cycle removal strategy based on sampling and combined with some simple gadget reductions, such as this splitting vertex technique in the previous slide. And eventually, they can reduce it to the C4 listing and approximate distance oracle problems. Here, the last step has some overhead, which is because the cycle count n to the 2.25 is still too large. Ideally, we want the number of C4s to be only n squared. This is a bound that is achieved by a random graph of degree root n. And if we could achieve this, then the last step can be implemented with almost no overhead. For this reason, the previous paper by Abud et al. Mentioned this open problem of improving the cycle removal step. However, in our work, we take a different approach. We take one step back and ask the following questions. Where do these C4s actually come from? So this all-edge triangle instance is produced by this Patraschu's reduction from threesome. So roughly speaking, this reduction encodes numbers from the threesome instance into edges in the graph in a way that the threesome solutions are encoded into triangles. And doing this way, we can naturally observe that the Sidon solutions in the threesome instance are mapped to C4s in the graph. So this means that if we start from a threesome with a lot of Sidon equation solutions, in other words, it has high additive energy, then after the reduction, it will contain a lot of force cycles, which introduces some overhead in the cycle removal step. So this is why our theorem 1 can be very useful here. So we plug in our theorem 1, which reduces from threesome to threesome on Sidon sets. And from there, we run the Patraschu's reduction, and we can achieve a cycle count of n squared. And then repeating the previous, the step from the previous paper, we can obtain better bounds for C4 listing approximate distance oracle. So to summarize, what we did is kind of switching the two steps of Patraschu's reduction and the cycle removal. So after this switching, then we're dealing with some kind of arithmetic cycle removal, which is removing Sidon equation solutions on a bunch of integers. So this has the benefit that there are more tools available for us to deal with numbers than on dealing with graphs. For example, we have some algorithmic tools such as FFT and also structural results from additive combinatorics. So this is why doing this way can allow us to get more efficient reductions. Now let's talk about the third application for LDT problems. So as we mentioned earlier, the threesome problem has a lot of variance where you can just change the coefficients in these linear three-term equations, and these are called 3LDT problems. And in most cases, you can use some folklore reductions to show that they are actually fine-grained equivalent. However, there's one variant that is kind of subtle. This is the average problem, where you're given a set of integers a, and you want to see if this set contains a non-trivial three-term arithmetic progression. So you can easily reduce it to threesome, but the other direction is much less obvious. In fact, this was an open question by Erickson in 1999, which asks whether average problem is also threesome hard. Here, the folklore reduction fails because they attempt to remove some fixed solutions by just shifting these numbers. However, this equation A plus C equals 2B is shift invariant and homogeneous. So these folklore reductions cannot just simply remove the fixed solutions this way. And very recently, these open questions was answered by Dudek, Gavrihovsky, and Starikovskaya, and they show that indeed the average problem is threesome hard, and actually their result generalized to other three LDTs as well. One way to understand their result is that they can reduce from threesome on an arbitrary instance to threesome on an average free set, which is a set that avoids three-term non-trivial arithmetic progressions. And from there, we can just use a folklore reduction to reduce it to average because now we don't need to worry about fixed solutions anymore. So now if we plug in our theorem 1, which reduces from threesome to threesome on the Seidel set, then again, we can also use a folklore reduction to reduce it to the Seidel problem, which asks whether a set of integers is a Seidel set. This is a particular kind of full LDT problem, and actually our result also generalized to other full LDTs. We show that under the threesome conjectures, all these full LDT problems also require a quadratic time. Let me briefly compare our result and the result by Dudek et al. So in the previous proof by Dudek et al., their main technique is some kind of masking idea, which gets rid of the threesome arithmetic progressions by taking the intersection with the baryon set, which is a very dense set that avoids three APs. So in our case, where we want to remove Seidel solutions, this idea no longer works because Seidel set in the interval of n only has density root m. And if we just simply repeat the step as in Dudek et al., then it will become very inefficient. So in our proof, we have to do something else, but this masking idea is still useful in one step of our proof. Now let's talk about the proof ideas for our theorem 1. So our goal is to reduce from a threesome instance with possibly cubic energy to a Seidel set. So the first step of this reduction is to reduce the energy from cubic down to a n to the 3 minus epsilon for some positive epsilon. And this step can be thought of as some kind of kernelization where we identify some additively structured parts and solve them and then remove them until we achieve a moderate additive energy. And once we have this tiny n to the epsilon gap in the energy, then we can use the random self-reduction technique for threesome and reduce it to a lot of tiny threesome instances. And by doing this, we can make sure that the number of remaining Seidel photopoles in these instances is very small. This was done using a special hash family that achieves almost linearity and also some kind of independence guarantee. But for some technical reason, these properties do not always hold, so we have to complement it with the masking idea from the previous work. And once we reduce the number of Seidel photopoles in these instances, then we can remove them using some kind of brute force enumeration. And eventually, we obtain these threesome Seidel sets. For the rest of the talk, I'm only going to talk about the first step, going from cubic to moderate additive energy. To understand this step, we need the notion of doubling of a set. We say a set of integers has small doubling if the size of the sum set of the set with itself is kind of small compared to the original size. So here we have an example of points that is very structured and it has small doubling and large additive energy. And here we have a random example. It has very large doubling and a small additive energy. So intuitively, if an input set of integers is additively structured in the sense that it has small doubling, then we can see that solving threesome on this set is very easy because we have these sparse convolution algorithms which can compute the sum set of two sets in output sensitive near linear time. However, in our scenario, where we have a large energy set, it's not necessarily true that it also has small doubling. For example, we have this simple example where we just take the union of these two sets, and this set has both large doubling and large additive energy. However, even in this case, we can still say something non-trivial about the set. We can see that this set contains a large subset that has a small doubling. And actually, this is true in general, and this is captured by the important result, Barlow-Semirati-Gowers theorem from additive combinatorics. It says that if a set has additive energy much larger than a cubed over k, we can think of k as some tiny polynomial in N. Then this set contains large subset that has small doubling. And in fact, this theorem can be made algorithmic by adapting the result of Chen and Levinstein, and we can find such a large subset with small doubling in n times poly k time. So using this algorithmic BSG theorem, we can do the reduction as follows. Given a threesome input A with possibly large additive energy, we take this, we have this while loop. While the energy is high, we invoke this BSG theorem, which returns a large subset A prime with small doubling. And then we find all the threesome solutions that involve A prime. And then we can simply remove A prime from consideration and continue with the remaining points. And we do this again and again. And finally, we we arrive at a set that has moderate energy. And the number of iterations is pretty small because each time we remove a very large fraction of the set. Now it remains to explain the algorithm for finding threesome solutions in A prime times A, where we know that A prime is a small doubling set. And so this is the formal lemma of our small doubling threesome algorithm. Suppose now we are having a three-part threesome, and suppose the first part has doubling constant k, then we can solve threesome in only k times n to the 1.5 time. So let's look at the special case of low small doubling set just for intuition. Let's say the set A is just a very dense set in an interval of constant times n length. So the doubling constant is constant. And so in this case, what we do is to divide the other two sets B and C into intervals where each interval has length order n. And then we have the following simple observation. If we take the group BI, then all the threesome solutions involving BI must have the third integer CI coming from this group CI. So it suffices to find solutions in A plus BI intersect CI. So this kind of decompose the threesome instance into a bunch of instances where each instance involves A, BI, and CI. And here, all the BIs partition the set B, and all the CIs, they do not partition the set C, but it's quite close. The sum of the size of the CI is at most 2 times C, because each element in C is only included in at most 2 CIs. So from there, we can use the very simple small-large distinction. For small groups, those groups with the size of BI at most root n, we just used brute force to enumerate pairs of integers coming from bi and ci, and the total time is root n times the sum of ci, which is root n times 2n. And for large groups, we know that the number of these groups is smaller than root n. And for each of these group, we use FFT to solve three-sum in near linear time. So the total time in this case will be n root n. To generalize this algorithm to the general small doubling case, where a plus a is smaller than k times a, we need to replace this FFT subroutine by the sparse convolution, as we mentioned earlier. And the other modification that we need is that we no longer use the simple decomposition based on intervals, but instead we consider several random shifted copies of A. So each of these copy A sub I is defined as A shifted by a random integer Si, and then we define the group Bi to be the shifted copy of A intersect B, and then we define Ci to be Ai plus A intersect C. So for similar reason, again, we only need to care about solutions in A plus Bi intersect Ci. So by choosing number of copies appropriately, we can make sure that indeed B is covered by all the Bi's. And at the same time, we can ensure that the total size of these Ci's is very small. It's smaller than k times n. On the previous slide, it was 2 times n, but here it becomes k times n. And from there, we can repeat the same large and small distinction argument and obtain k times n root n running time. Here, I omitted some details about how to actually construct these sets Bi and Ci efficiently. To do that, we need to change the sampling process to something slightly smarter. Finally, let me mention one additional result. For details, please look at our papers. We show that the triangle detection problem has some superlinear lower bound based the stronger version of three-sum hypothesis, although our lower bound is not tight. Now let me mention some open questions. First, can we get tight lower bounds for approximate distance oracles? Currently, we have a factor of 2 gap on the denominator on the exponent. And the second question is, can we show foursome hardness for the problem of deciding whether the input set A is a Sidon set? So currently we know how to show threesome hardness, but for foursome hardness, it's not clear because the self-reduction for threesome does not work for foursome. Thank you very much.